All right, thank you. Let me begin by thanking the organizers for having me here. I've really enjoyed the talk so far. So as we just learned, I'm going to be talking about an application, sort of an off-the-wall application of tensor networks to designing better image compression methods. Okay, so the genesis of tensor networks was as a means to better describe quantum wave functions. Okay, so describing a quantum wave function fully is sort of very expensive. So one way to think about tensor networks is as offering a compressed representation of wave functions. Okay, but thinking about things in this way, like you may ask the question, like, have the methods we've developed for compressing wave functions, are they useful in, say, math and science? And it turns out there are very many applications where this very nice formalism of tensor networks could be useful. So we've already seen several talks about machine learning. I have worked with one of my students, Aaron Stayhill, in using tensor networks to reconstruct missing data from a data set, so data completion. But today I'm going to be talking about tensor networks, their use in designing better data compression routines, specifically focusing on sort of image compression. And this is work with James McCord, an undergraduate student at Georgia Tech that we're in the final stages of writing up. Hey, and hopefully what I want to express today is that just by using sort of the very standard tools we've developed in tensor networks, so very familiar things to everyone who's worked with tensor networks, by taking them to this other setting, talking about wavelets, we can actually do some really nice things and actually improve on the state of the art in quite significant ways. Okay. So I'm going to begin my talk just by giving a sort of brief introduction to what wavelets are. Then we're going to talk about how they relate to tensor networks. And then I'm going to talk about the work itself, where we use this relation in order to sort of try and improve upon what can be done using this technology. Okay, so everyone is familiar with Fourier transforms. Okay, so taking a momentum space representation of some data. Okay, so wavelets were developed relatively recently, like in the 80s and 90s, as a compromise between real space and Fourier space representations. Okay, so a wavelet is like some kind of small wave packet. So it's localized in space and is designed in such a way that it occupies a sort of narrow band and frequency space as well. Okay, and so a single wavelet is a local wave packet, but what we really want is a wavelet basis, so a set of these wavelets to form an orthogonal basis that we can expand any function in. Okay, and we make this by having translations of some sort of local function as well as dilations. Okay. If we're on a lattice, so these are just sort of discrete translations and some form of discrete dilations. Okay, there are many different types of wavelets. So I'll just give you an example of the simplest non-trivial ones. These are called Dobushi's D4 wavelets. Okay, so this is what the Dobushi's wavelet looks like at the lowest scale. And you have translations of this by I think 2 sites. So we have if we have an n-dimensional vector space or an n-site lattice, we have n over 2 of these lowest level wavelets. At the next scale, we have n over 4 of these these dilated wavelets. At the next scale, n over 8, and we keep sort of going this way. And then this complete set of this set of functions in its entirety represents an orthonormal basis. Okay, so it's a unitary change of basis that we can expand any function on the lattice can be represented as a unique linear sum of these wavelets. Okay, and it's really and in doing this sort of decomposing a function into its wavelet basis, we're really sort of resolving information at different scales. Okay, so the ones sort of down the bottom, they represent the short scale information in my function. The ones up, the more dilated ones represent the the large scale information. Okay, just to give you a very, very quick rundown of how we actually make these wavelets. Okay, so you have some auxiliary function you build first, which is called a scaling function. So it's defined in terms of, say, some sequence, which I've drawn here. And then this defines some recursion relation for how I build wavelets at larger length scales. Okay, so the wavelet at larger length scales is built by taking a linear combination of the ones from the previous scale according to the coefficients in my scaling sequence. Okay, so by repeating this procedure, I can build these scaling functions at different scales. Okay, so some kind of recursive relation. And then the wavelet functions are built from these scaling functions, okay? So taking some appropriate linear combinations of the scaling functions at each scale. Okay, so yeah, so we have wavelets, so we have scaling functions, which is some sort of auxiliary thing, and the wavelets themselves. Okay, so how this works as a transformation. So what I'm imagining is, so I have some initial function. I want to express this in a wavelet basis. So I do this in a sequence of steps. So in practice, it essentially works as a convolution where the convolution with the lowest level scaling functions sort of captures the low frequency information of my original function. So it's acting as like a band pass filter where we have a low pass and a high pass filter, and the convolution with the wavelets captures the high frequency information of my initial function. And sort of I repeat that procedure again on this low frequency part as well. Okay, so from the physics perspective, this is very reminiscent of coarse graining. We take some original theory and we sort of integrate out the high energy degree, or we integrate out the high frequency degrees of information. What we're left with is some sort of the low frequency or long range part, and sort of we can repeat this procedure iteratively. Okay, so it looks very similar to things we're familiar with in physics, coarse graining, renormalization, that kind of thing. Okay, so this is for a 1D function, but we can extend this to 2D functions or images. Okay, so I've drawn, we have a nice photograph here, and we've done a 2D wavelet transformation. Okay, so the image expressed in the wavelet basis is above, and you see that it has this fractal structure. As we move towards the top left, we're sort of, this is the larger scale information about this image. Okay, so down the bottom right is the short scale information. Okay, so we've basically taken this image and we've resolved its components at different scales. Okay, and in this wavelet basis, I've used sort of the bright pixels to represent the large wavelet values. Okay, so you have a large wavelet, a large component whenever the image is changing sort of relatively quickly. Otherwise, if the image is relatively smooth in a place, then the wavelets are designed in such a way that the coefficients will be close to 0. Okay, and just to be clear, this transformed image is just a unitary transformation. So we still have all of the information at this point. Okay, we've just changed the basis that we represent the image in. Okay. So there are huge, many different applications of why we want to consider wavelet transformations. One of the most important applications is towards compression. Okay, so this could be image compression. It could also be sort of video compression as well, or audio compression. And there are many sort of standards in use based upon this type of transformation. Okay. So how does this work in practice? I can just give you a simplified rundown of how we build a compression routine based on wavelets. Okay, so I have my original image. I transform into a wavelet basis. And as we said, like if the image is relatively smooth in most places, then most of the wavelet coefficients will be very small or close to zero. Okay, so I keep only a small number of the coefficients and I throw away the rest. Okay, so I have, I'm in this case, I only keep 1% of the coefficients. So I have a very high compression. At the same time, if I do the inverse transformation, I have something which is still relatively high fidelity. Okay, so if you looked very closely at these two images, you could see some loss of detail in the recovered image. However, it's still very good in this case. Okay, so in short, like most images you could have, or most sort of images of real life, are going to be relatively sparse when represented in a wavelet basis, just because of the way wavelets are constructed. Okay, so you only have large coefficients when your image is changing sort of relatively quickly. Okay, so that's kind of a very, very quick rundown of what wavelets are and why they're useful. So now we get into some more physics, which is how are these things related to things we're familiar with, like tensor networks. Okay, and so what I've drawn here is we have a mirror quantum circuit, a type of multi-scale tensor network that sort of widely used, and I've drawn it next to this decomposition of an image in terms of this multi-scale structure. And you can see it kind of, you have some very very obvious similarities between sort of this tensor network, which sort of resolves the quantum state into its information at different scales, versus this discrete wavelet transformation. Okay, so they're clearly like very similar, but the question is this a superficial similarity, or is there something deeper with this connection? Okay, and this was sort of some work I did. So Steve White was the first one who sort of noticed this connection between mirror and wavelets, and this was some work I did with him a few years ago. And it turns out that there is a really precise connection between these two things. It's not a superficial connection. In some sense, these two things are exactly the same. Okay, so discrete wavelet transforms are exactly equivalent to Gaussian mirror tensor networks. Okay, so earlier we saw that a wavelet transformation was sort of defined by this recursion relation between scaling functions. It turns out that the unitary circuit that mirror is based upon exactly, or can exactly describe the same recursion relation. Okay, so you can implement your Dobushi's D4 wavelets rather than thinking about them as these functions that live on the lattice. You can implement the transform directly as a quantum circuit if you like. It's exactly the same thing. Just to be a bit more clear, though, we're working in a direct sum structure rather than a tensor product structure. Okay, so when I draw this circuit as this set of gates, we're really thinking about a matrices built from a direct sum of local gates. Okay, and this is sort of precisely the type of tensor network we use when we're describing Gaussian states or free fermion states. Okay, so we'd already made extensive use of this type of tensor network for describing free fermions. Okay. So in this case, like if I have a 2x2 unitary matrix, I have one free parameter, so I have a free angle. If I build a unitary circuit, if I fix the two angles that I have, so in U1 and U2, if I choose them in a certain way, so pi over 12 and minus pi over 6, then the circuit that I build from these gates is as I said, it's exactly describing a Dobushi's D4 wavelets. Okay, so if I made a big matrix by contracting all of the circuit together, then the columns of this matrix would just be Dobushi's wavelets. Okay, so the Dobushi's D4 wavelets are exactly the same circuit structure as a mirror. In this case, it is what we call a binary mirror. So we can exactly describe these functions through some appropriate choice of these gates. And it turns out higher order wavelets, okay, so the next level is D6 Dobushis. These can also be described as unitaries by unitary circuits. We just need, for instance, maybe an extra layer of gates in each, so an extra set of gates in each layer of the mirror. Okay, and then so that's sort of the very quick breakdown, but these these multi-scale tensor networks, when working in a direct sum structure, are exactly equal to discrete wavelet transformations. Okay, so so this turned out to be very useful in describing a bunch of physics. But what I want to focus on today is saying how this can be used to actually, how our knowledge of tensor networks can be used to build better wavelet transformations. We had a question.
Do you mind asking a question by J.N. Landsberg?
Sure.
Okay. So.
Hi, thanks. I'm a little confused. Are you saying that you're getting all mirror this way or just some subset of them? Because you have a kind of continuous unitary thing in the tensor network world. And what does that correspond to in the Dobushi's world?
So mirror, you have these like free parameters in each of your tensors. What I'm saying is that there is a particular choice that represents the Dobushi's wavelets. If you took another set of angles, you would have a set of wavelets, but they would not correspond to these known ones.
Okay, I got it. Thanks.
Thank you. Okay, so how do we leverage our knowledge of tensor networks to do something that the wavelet community has not been able to do? Let's have a look. So first we should ask the question, what wavelets are good for image compression? So if I take these Dobushi's wavelets, they form an orthogonal basis. However, they're not symmetric, so spatial symmetry turns out to be important for a lot of applications. And in practice, these don't compress so well. There are these other wavelets called coiflets, which are orthogonal. They're much closer to being symmetric, although not quite symmetric. They turn out to compress a lot better. There are these other wavelets called CDF wavelets that now we've sacrificed orthogonality, so these no longer form an orthogonal basis. However, they are symmetric and they work really well in practice. You can also try other things where you have orthogonality and symmetry together. So some scale 3 wavelets, I'll explain these more later. But however, all attempts at doing this have turned out to sort of work really bad in practice. Okay, so in terms of adopting a wavelet for practical use, most algorithms use these CDF wavelets, sort of all of the standardized methods. These turn out to be sort of a good compromise between all of the properties that you want. And the compression sort of works, I believe, is the sort of the best known compression in practice. Okay, so what we're going to do, and again, this is some work with Steve from some years ago, we're going to use our tensor network, our skills, our methods to try and construct new wavelets. Okay, and we're going to follow an approach which is very, so this is the same approach we use when applying tensor networks to a quantum system. So you first sort of think about the geometry of your network. How do I, which tensor network geometry do I want to use? Then you think about imposing symmetries on your network. So which symmetries are important? How do I impose these symmetries on my tensors? And then you have some optimization of like the free parameters according to whatever sort of system you're trying to model. Okay, so we're going to take exactly the same approach, but using it to build better wavelets. Okay, so first we're going to choose a network structure. In terms of, say, designing mirror, so I worked a lot with mirror in my PhD, and this was something we looked at extensively, is the different types of circuit I could construct. So these represent sort of different rescaling factors, different organization of the blocks, different causal structures, and sort of these have some common properties, but also differ in their fine details. Okay. And so we try and do the same type of thing with wavelets, where rather than the standard binary circuit, we explored many other types of unitary circuit. Okay, so there are many different ways you can try and compose these gates and build layers, represent this hierarchical transformation. Okay, so these are all essentially types of wavelets. However, they may differ from sort of the established notion of what a wavelet is. Okay, so they can represent different scaling factors as well as sort of different translational and blocking properties. Okay, in practice, what we settled with, or what I will talk, so we explored many options. What I'll talk about today is what we call a ternary unitary circuit. And this is actually a straightforward generalization of the ternary mirror. Okay, so we call it ternary because it represents a 3-to-1 rescaling transformation. Okay, and in terms of mirror for quantum systems, the ternary mirror is actually greatly preferred over the binary mirror because it has some nicer features. So it was actually, so I think it's interesting that in the case of the wavelets and the quantum circuits, as you'll see, the ternary unitary circuit also has some nicer features as compared to the usual ones based on a binary circuit, a 2-to-1 rescaling. Okay, so we're using this this novel type of circuit structure. Describing these types of wavelets would be very difficult if we didn't have this nice diagrammatic notation. If we're just describing functions on the lattice, it would get very complicated very quickly. Okay, so we've chosen our geometry of our network. The next thing we want to do is impose symmetries on our network. Okay, so we want wavelets that we want a wavelet transformation that is orthogonal. So all wavelets are orthogonal to all other wavelets. We want wavelets which have reflection symmetry as well. Okay, so these turn out to be very important for practical applications. So we have these global symmetries. How do we apply global symmetries on tensor networks? This is something that any student who works in this should be able to answer. If you want to impose a global symmetry on a network, you impose it by imposing some local constraint on each individual tensor. Okay, so that's what we do here. So we want orthogonality and reflection symmetry. If I have a 2x2 matrix, there is only one example, one non-trivial example that satisfies these two constraints. It's a swap gate. If I have a 3x3 matrix, however, there is a one parameter family of these matrices which are both orthogonal and preserve reflection symmetry. Okay, so this is why we wanted to do a ternary circuit with these 3x3 matrices, is to have these 3 degrees of freedom that we can work with. Okay, so if we're just doing 2x2 matrices, this is impossible. Okay, so We've chosen our circuit. We've figured out how to impose symmetries on our circuit. We still have these free angles that we're able to choose at our discretion. Okay, so the final step is, again, one very common to anyone who's done tensor networks. We optimize the free parameters in our circuit according to some loss function. Okay, and we have very, very good methods that have been developed for doing this kind of numerical optimization. So it's really not a big deal. Okay, and the loss function we use is based upon making sure sort of each layer of the network is sort of well separated into low, mid, and high frequency components. Okay, so we want to realize a sort of bandpass filter with these three sort of separate frequency components. Okay, so we do this optimization. I've drawn sort of the wavelets we get. So we have two wavelets and a scaling function. When we display these in frequency space, we see that these are sort of well localized in the frequency space. We have one which is really the low frequency one, the one on the left, a mid frequency one, and a high frequency one.
So Glenn, just to say, you have about 5 minutes.
Thank you. Okay, so we used our standard tensor network methods, and we came up with some new wavelets. So here they are in the sort of large scale limit. They look very nice, very smooth, very compact. If you've seen wavelets before, as compared to other attempts to build wavelets with the same symmetries, ours are much nicer. So by leveraging this tensor network technology, our circuit understanding, we were able to do a much better job as compared to sort of previous wavelets were very jagged and sort of very spread out and just not very good in practice. Okay, so and then I've been working with James McCord, who's a student at Georgia Tech, who's been doing a really good job in sort of testing and evaluating the performance of these wavelets. And we're almost finished writing a paper about this. Okay, so this is our transformation of in the usual from the previous wavelets. Our method for compressing using the new wavelets looks very similar, although because we're based on a 3-to-1 scheme, we have this sort of 3-to-1 fractal structure. Okay, so what we're going to do is take a test database of many thousands of photographs. We're going to compare how well our wavelets compress versus these CDF wavelets, which are sort of the state-of-the-art wavelets used in practical applications. And the way we're going to do this is we're going to say, what is the minimum number of coefficients in order to achieve some desired quality? Okay, so here is the comparison. So we're looking at how well our wavelets work compared to the established state-of-the-art wavelets. Okay, so this is anything in the plus axis denotes an improvement in efficiency. And you can see we have all these sets of different types of photographs. So each of these is a set of many, maybe hundreds of photographs. And what we can see is that the new wavelets we've developed are consistently better than the established ones. Okay, so on average, we have 7% more efficient compression. And these are sort of these are photographs of all types of things, all size photographs, different amounts of detail. Yeah, and we sort of have a very consistent, nice improvement. Okay, and this advantage of our new wavelets becomes even greater if we demand even higher quality fidelity. Okay, the gap increases. So this type of thing could be very useful in something like medical imaging, where a scan generates a huge amount of data, but you still want to keep like high fidelity representations of your images. This would also be very important in video compression, where if I'm streaming content from the internet, a 7% reduction in bandwidth would be sort of very appreciable. Okay, so let me just summarize. So as compared to the previous sort of best wavelets, we've developed some new wavelets using tensor networks, which have some very tangible advantages. Okay, so we have better symmetry properties. We're orthogonal and symmetric, and we also do a better job of compressing data than the established wavelets. Okay, and I regard this work as really sort of a first attempt to take tensor network technology to this setting. There are much more advanced things you could do that we know how to do, such as, for instance, we could try and tune the angles in our network specifically tailored to a certain data type. Like if we were interested in medical images, we could try and find wavelets specifically tailored for medical images, sort of using our standard optimization. Okay, so I think this is a really nice example of taking some very standard tensor network stuff, so stuff we're all familiar with, applying it to a new setting and actually seeing we can do some really interesting and really nice things using tensor networks outside of physics. And as I said, there are many more applications in data science that people are also exporting this type of technology to. All right, thank you for your attention.